today is the concept of hashing and some analysis of hashing, exactly what this is, different ways to implement hashing algorithms. Anybody familiar with hashing? Nobody, except for one guy? All right. So people think it's a good breakfast food. Eggs and hashing. All right, so hashing is basically an interesting concept. Basically, what we want, the reason we have a hashing algorithm is because we'd like to find things very, very quickly. It's useful for finding things very quickly in memory. Now, we know the memory of a computer is very fast. It's very, very fast, and the primary memory is going on the speed of billions of a second. So if it takes you 3 billionths of a second or 15 billionths of a second, it's still pretty fast. But that's the speed of memory. So if we need to randomly find an element in a large array, we can find it very, very quickly in a matter of billions of a second. The speed of secondary memory, like a large disk, whether it's an SSD or an HDD, meaning if it's a hard disk drive, right? What's SSD? Solid state. So solid state has got better performance. It's got some other issues, but in any case, solid state tends to be faster, but it tends to be smaller. And hard disk drive tends to be much bigger, gigabytes, terabytes, petabytes, but it tends to be slower. Accessing an hard disk drive, HDD, is on the order of milliseconds, which if you compare to billions of a second, which are nanosecond, is 1,000,000 times slower. Really, a million times slower. That's a huge, huge, huge difference. So if we need to look through a file, search a file, it would take a very long time to search through a file because you're talking about, I'm talking about a large file now, because you need to access this data and search through this data and move this data into memory, then move the memory into the CPU, search through it. It's a very slow process. CPU wants to go at billions of a second. The HDD wants to go at milliseconds. That's not compatible. Those two things are not compatible. So hashing is kind of a way of trying to find things without having to look everywhere for them. So if we imagine a large array or a large file, if we do a linear search meaning that we look through all the elements, we can say the complexity of that is going to be like big O of n, right? It will take us n, roughly speaking, n comparisons or operations. Now, if we're talking about an array, that may be okay. If we have 1,000 elements or 1,000,000 elements, and it takes us nanoseconds per element or so, it's not too bad. We can find it because processors are very fast. But if we need to look through billions of bytes on a disk, even at SSD or HDD, then it may be prohibitive. It may take minutes, hours, or even many hours in some cases to do a linear search. Imagine searching an entire file with 16 gigabytes. Wow, that would be crazy, right? But you need to find something. So linear search is good for some cases, not good in other cases. Binary search gives us a better performance, but it requires what? The data has to be sorted, right? So therefore, if you're going to go in the middle and say, okay, I'm only going to look here, or the reason you're looking here is because everything from here is bigger and everything from here is smaller. I'm looking for bigger, so I'm going to look here. You can't do that if the data is not sorted. You can't do that if the file is not sorted. You can't do that if the array is not sorted. But if it is in order, then you can do it. So binary search gives you better performance, log n, and log n tends to be an outstanding complexity for memory-based algorithm. By memory-based algorithm, I'm talking about memory, primary memory, RAM. If we're talking about large files, well, it might not be as good. Because, for example, what does it mean log n when something has, for example, 16 gigabytes? Log n, what's log n of 16 billion? Well, billion is 2 to the 20th, right? 16 is 2 to the 4th. So we're talking about 2 to the 34th. So that means we're going to take 30 or so operations, each of which is going to be running at HDD speed, which is milliseconds. So we could be running into minutes just to locate something, even at this amazingly efficient algorithm complexity. So even though it's much, much better than linear, it could still be a disaster for large data on file. Another approach is to use something called a hierarchical index, which we'll talk about. Hierarchical index essentially is an index where you start looking for something. Let's say, again, I'm gonna make use of the idea that we're searching a very large file. Maybe it has 16 billion records, gigantic, very, very large. Each record could be a K, right? So it's very, very large. So we start looking at some index, and the index says, okay, what you want to do is you want to go to this location to search further. What you want to do is go to this location to search further. And finally, you get to some point in the index, and the index says, why don't you look at this address? And then to look at the address, then we go to our file, and we seek within the file to that location where we hope to find what we're looking for. So that's a hierarchical index. Hierarchical index is something slightly different from linear index. A linear index is basically, the whole index is sort of a linear structure. Hierarchical means it's kind of more like a tree structure. And you know the advantage of trees, right? Especially if you have a binary tree, if you go to the left, everything's smaller. If you go to the right, everything is bigger. So if you could imagine an index into a set of records. For example, if you had a binary tree, and that binary tree was full, we love full, easy to analyze, and each node in the binary tree had a reference to a record in the file. And there were 1 billion records in the file. Then that balanced binary tree would have what height? Well, 20 would be, first of all, what's a K? 2 to the 10th. What's a meg? 2 to the, it's a K times a K is a meg, right? So it's 2 to the 20th. And what's a gig? It's a K times a meg. So 2 to the 30th. So we're talking, so the tree height would be 30. Let's think about that. So the height of the hierarchical index, which is a binary tree, would be 30. I would start here. At the root would be what key? This root in the tree would reference which key? The middle of the file. Okay, so it would be the middle of the file. Now where is it in the file? Oh, we don't know that. Is it in the middle of the file? Not necessarily, because maybe the file is just coming in at random. In chronological order, data comes in. This happens to be the middle element, but maybe it's at the end of the file, because it just came in yesterday, and everything has been accruing for a month. But the last one came in, we just tacked it on here, but in the tree, it's in the middle. Why? Because 50% of the data is smaller in key, 50% of the data is bigger in key. So you see what I'm talking about? So that's how we're going to do it. So if I'm looking for something that's smaller than this key, then I will go to the left of the index. So this tree has 1 billion nodes. But by moving left, I've already skipped 500 million. It's a really efficient move. In fact, each time I go down, I take out half of the remainder. So moving moving one down takes out 500 million, which leaves you 500 million. Moving to the left or right, again, takes out half of that half, and et cetera, et cetera, et cetera. Eventually, at the very bottom, if I go all the way to the bottom, I'm going to make 30 comparisons, which is pretty fast. Well, it's pretty fast if you can imagine keeping that index in memory. But can we really keep that index in memory? If we have 1 billion keys in the file, and let's say every key corresponds to a K bit of information on that file. So a key is connected to a K bits of information, bytes of information. So, if that's the case, then once I take the number of keys, which is 1 billion, and I multiply it by another 1,000, now I'm talking about 1 trillion. So now I'm in terabytes. So there's a terabyte size file, is what I have. Because a gigabyte index with each key corresponding to a K of data is a terabyte file. right? A gig of records, a K each terabyte. So the question is, can I keep that file in memory? Well, I don't know. The answer would be yes, if I could fit the entire contents of the tree in memory at the same time. Let's see what it is. It's going to take 1 billion keys. That's a gig. And how big is each key? Well, each key, I would say, is 32 bits. Is that fair enough? 32 bits, that's how many bytes? 4 bytes. So that's 4 bytes. Okay. Now, in order to make a tree, the tree also has to have pointers, right? Unless we use that really clever technique that we used yesterday with complete trees. If we're so lucky. That would be really nice because then we could save all that room. But we're going to assume we can't do that. So that means that you're going to have to have a left pointer and a right pointer. How many bits do you think a left pointer takes?
32 bits.
I'd say 32 bits, which is 4 bytes. So we got a key, left pointer, right pointer. How many total bytes for a node then?
12 bytes.
12 bytes. But we had 1 billion keys. So that's 12 gigabytes. How many of you have a machine that has 12 gigabytes available for a tree? You do?
I guess 16 gig of RAM. I mean, that's close. Right?
How much? How much?
16 gig of RAM.
Okay, but can you use it all for one program? Unlikely. Remember your program, we'd like to be able to think we can, but if you ever look at the set of processes running on your computer, you're going to be like, oh my gosh, I forgot about the operating system. That's up there. Even if you close everything out, you still got all this up running. So it's very unlikely that you can keep the whole thing in memory, because basically it's just not what is efficient computing. That's not what efficient computing does. In fact, if you were to try to do that, you would have to write some very special instructions to the operating system begging for that much RAM for your runtime system, regardless whether it's in C language or Java or whatnot. It would be very hard to allocate that much more memory. And of course, if you could, then I'll just double it and say, okay, I can't do that. So the bottom line is, it's unlikely that we can fit that whole tree into memory, or even a large portion of the tree, nor maybe is it a good idea that we should even try to do that. And I'll tell you why. Because if that tree truly has 1 billion nodes, then the bottom level has 500 million of them. Which means that if I were to eliminate that bottom level from memory and keep it on a file, I would require half as much as I initially thought I'd need. So from 12 billion to 6 billion, right? The way I'm saving a lot of stuff. Now, why would I want to do that? Why would I want to eliminate that bottom layer from the tree? When in reality, the probability is that 50% of the time I'm going to have to go to that bottom level. Because 50% of the nodes are there, therefore 50% of the records are referenced to there. Why would I want to do that? And the reason is because I don't want to have to make 30 references to secondary memory, but I don't mind making 1 or 2. Because that's, again, milliseconds. It's not super fast, but it's not like it's going to be a minute or 2 minutes. So I could eliminate part of that tree as much as I want. I could sort of make a trade-off. I could keep some of it in RAM, keep some of it in secondary memory. And we'll see how that works. It sounds very exotic, but it's not that complicated actually. Okay, so that's one of the reasons. So now, what do I mean by hierarchical index? Well, so a binary tree could be a hierarchical index. It's never done that way. In reality, if I really had 1 billion keys, I would never use a binary tree. Why not? I'm adding keys in random order into a file, and I'm keeping an index as a binary search tree. Why would I never do that? Tell me a reason. You know a lot about trees. Why would I never do that? Any idea? Is there a guarantee that the tree I'm going to create is going to be balanced? No. No. So therefore, I have to assume that the tree I'm going to build is going to be what? What will be, do we have any idea what the average depth of a node will be of a randomly generated binary search tree? The answer is yes. and the answer happens to be 1.38 log 2n. So on average, with a billion, I'd expect to have, what would be the average depth? Well, the average depth, what would be the best depth for a billion? We just said it a minute ago. The best depth for a billion would be what? 30. 30. So that means the average is going to be 1.38 times 30, which means 40%. Let's call it 40%. 40% of 30. What's 10% of 30? 3. So 3, 6, 9, 12. So 30, so 42. So right away, my tree on average is going to have a depth, an average depth of around 42. Not terrible, but it's 42. That's a lot. I'd rather have something like 3. How could I do that? How could I have a tree with the same number of keys and only have 3 as the average number of comparisons to get what I'm looking for? How can I do that? What would I have to change? What kind of a tree would that be? And that is almost a pun on the answer, but it's okay. The answer is it would have to be a tree with more than 2 children, or no. It would have to have a higher order. Yeah? And we'll talk about those kind of trees in detail. Okay, let's keep going. So, but we are going to skip through all that stuff right now. We're going to go directly into hashing. So hashing basically says, okay, this gives me a linear search complexity, big O, which may be very bad. This is big O log n, but could be very bad for extremely high, large search spaces. And this is OC, where C is some constant. It's really not a constant. It's really a function. For example, it could be log base 2 of n comparisons. But we're going to make trees so dense that for huge problems, our function will only grow to like 3. For billions and trillions, it's going to be 3. So we can think of 3, you know, if that's a realistic problem, that's a large problem, then essentially acts like a constant. So I'm using the idea of a constant, where a C is the number of levels in the index. Of course, can we do any better than that? I don't want to pay n, log n, or even a constant number of memory accesses. I want to access my data in constant time. I want to have theta 1. So none of those previous algorithms give us that opportunity, but one technique that tries to do that is hashing. And so the ideal complexity of computation of data location is big O of 1, theta 1, constant time. Same number of, the same cost, regardless of the size of the structure. The same cost. That sounds pretty good. So right away we're signing up for it. Okay, where do I sign up? This is good. Now, let's look at an idea. Let's say we are going to store, we'll look at the basic idea, we'll look at the perfect idea, and then we'll realize why the perfect idea is not always suitable. But when it's perfect, it's really perfect. So we want to store 25 keys. Okay? I have 25 records that I'm storing someplace. Each of those keys has a number, and the numbers range from 0 to 999. So 3-digit number. Okay. So what I'm going to do is I'm going to create a hash table. The hash table is basically think of it as a big array. And in that array, you have your records. So think of a hash table. Why do we call it a hash table? Because we are going to hash into it. We're not going to search it. We're going to sort of just figure out a magic location and just go there. All right? So each hash table has a key field and a reference field. So the hash table has 2 parts, really, the key field and the reference field. The key field is the key of the record, and the reference field is exactly where that key is located, let's say on a large file. Okay? So we'll initialize 1,000 hash table locations to -1. And -1 just means invalid key, because the keys have to be non-negative up to from 0 to 99. So we'll do that. And then we'll store each key into location of hash table sub I. So if the key is 255, then it'll go into hash table 255. So if I'm looking for key 255, I'm simply going to index into 255 and I'll find it without searching for it, right? So if I'm looking for key 255 and I go into hash table 255 location, I will look for two things in that slot. The key, what does the key have to be? 255. And what does the reference have to be? The location where I can find it. What does that mean? The location may be in the file. Where is it in the file? Oh, it's offset. 35,265,211. Go there, you'll find it. I can get there quick. Just seek in the file, I can do that. So we're going to store each of them. So now, what happens if I'm looking for key 255, and I go to location 255, and the hash table contains a -1 in there? What does that mean? Doesn't exist. In fact, I initialize all of them with -1s, and I only change them to the key value after they've been stored. So if I search for something and I get a -1 in the hash table entry, it's not there. That's easy. Would you agree that this is theta 1 complexity for search? Because there's no other, I'm just going to basically do, now what exactly does it mean hash table sub I? Well, some of you know how that works, right? Hash table is an array. Sub I means it takes the address of the array, adds that offset, goes there and gets that from memory. Dereferences that value as the record that we're searching for. That's how it works. Okay, so 25 of the 1,000 records are valid, all the others are invalid. Would you agree with that? Because I only have 25 records. So that means 975 of them have -1s in them, but that's the price I'm paying for theta 1 access. So our hashing function, h of I, is simply h of I returns I. So if you want to find a key 55, then hi returns 55. Very simple hashing function. Hashing function returns where you to search for things. This hashing function is as simple as it gets. So we could call this, in a sense, perfect hashing. It's perfect hashing because we are guaranteed of constant time access to a record for storage and for retrieval. This is too long. Okay. We already know that. Okay, so here you can see the example of a hash table. So you can see that some of the values may be -1, some of the values are not -1s. That means this key exists, this one does, this one doesn't. If it exists, that's a reference. And the reference, again, the reference could be, typically what we're talking about is an offset to a file. If you open a file, there's a file pointer that immediately starts at offset 0. What does that mean? 0 bytes from the beginning of the file. And as you read the file, or as you seek into different locations, it can move you to different parts of the file. That's the way computer science people like to think of a file. They like to think of it as a big, contiguous block of memory. It's a really nice way to think about it. It's completely not the way it is, but it's a really nice way to think about it. In fact, the file is strewn all over tracks and sectors and cylinders, and it's really messy, and there's a table on the disk itself that tells the disk controller how to find the next part of it. But it's not for us to worry about. We're computer scientists. Computer engineers, they have to worry about it. All we care about is that when we seek to offset 2 million, it gets us, logically speaking, 2 million bytes after the beginning of the file. And every time we do it, we go to the same place. So we're happy with it. It's consistent. So let's leave it at that. Thank goodness for the good, efficient hardware that does that. So the hashing function satisfies the big O requirement for the immediate lookup. The hash table implementation is not very space efficient. You might argue that 97.5% of the slots in the hash table are never used. That's a downside. So we have some wasted space, but we have that efficiency. Now suppose we had a different problem. We had 500 employees in a company, let's say, so N is 500, and each one has a social security number. Now I need to store the social security numbers as the keys, because that's a unique identifier. I'm going to use that as my unique identifier as a key. How many digits does the social security number have? 9. Maybe yours is 10, sorry. I think it's 9. So, if it has 9, is it 9 or 10? It is 9, okay. Maybe think about it.
3, 2, 4, right?
Yeah. It's 9. So therefore, now each of the digits in your social security number goes from 0 to 9. So there's 10 of them. So total possible social security numbers, all the social security numbers are basically, how many of them? Let's count them. Each one is 10 times 10 times 10, so it's 10 to the 9, which is exactly a billion. Wouldn't cut it in China or India, right? You need more than that. 1 billion wouldn't be enough. But for now, we're good with a billion, so eventually we'll have to do something about it. But the bottom line is, in order to guarantee perfect hashing for these 500 employees, I would have to have my hashing table have how many slots? A billion. You see the problem here? A billion. And how many of them would be empty? Well, all of them but 500. So we would have a hash table with 10 to the 9 key locations, so that we could store each unique location for a possible social security number. And so therefore, our waste of space would be 0.9999995. It doesn't seem like a good idea. It doesn't seem like a, so imagine that so this is a billion. Now, what would have to go into the slot? Well, I guess your social security number, which is 9 digits, which I suppose we can store in 9 bytes if we wanted to. And then we have to have some kind of a reference. So let's call it 12 bytes. So 12 billion bytes would be used for this table. But actually, we only use about a K, about 10K or 100K. Does that make any sense? No. So it gives us perfect hashing, but the cost, the overhead of actually doing it puts us into a ridiculous situation. So we're going to try to be more flexible. We're no longer going to require that every single key has to have a unique location where it goes or nobody else goes. We're going to say, we're going to be a little bit more friendly. We'll keep a hash table such that when somebody has to be stored, some key has to be stored into the hash table, it will have a very high probability of going there without contention. Because it's possible that maybe another key will also go there and try to get in there. And that could be a problem. We call that a collision. So we're going to change our function to a very simple change. And the simple function is hi. The hashing function of I is going to be I modulo 25. So I modulo 25 will always return a number between 0 and 24. It's the remainder when we divide by 25. So you can see over here that h of 52 returns 2. Because when you divide 52 by 25, the remainder is 2. So it makes sense that 52 can go into location 2. Okay. 49 goes into 24. Okay. 273 goes into 23. You take all the factors of 25 and the remainder is 23. 500 goes to 0. Because when you divide 500 by 25, it's an even number of times. It's an integer number of times with no remainder. The remainder is 0. So it goes right there. So it sounds like a good idea. So now our table is much, much smaller. But there are some situations that we could have problems. And specifically, if we try to hash 273 and 73, they would actually indicate by the hashing function to go to the same location, because the modulo of 25 on those two are exactly the same. So there's a set of keys which will return the same hash table location, In fact, those keys are any multiple of 25, any multiple of 25 plus 23. So that starts with 23 when I is 0, goes up to 48 when I is 1, 73 when I is 2, etc., etc. When I is 10, it's going to be 273. That's what we saw before. So in general, we will have 1,000 divided by 25 key values, which will return the same location. But it doesn't mean that we're going to have those keys in our collection, but they could happen. So the idea of hashing is, we like the idea of it, but we're scared about the worst case scenario. But because we are algorithm students, we're not going to be scared of the worst case scenario because we're going to be more interested in what?
Average.
The average case. What is likely to happen? What is likely to happen? That's what's interesting to us. Now, typically when we create a hashing situation, we do not know in advance what the keys are going to be. So therefore, the only way we can actually find out whether our hashing function is going to be efficient is we'll try to make a simulation, generate a set of keys that may look like the future keys, and to see what the performance is going to be. Let's say you're going to use as input last names of employees and first names of employees. One thing you can do is maybe you take a phone book and you take, let's say, randomly select 200,000 names, first names and last names, and then try to hash them using a hashing algorithm and to see how many collisions you end up having. How many times does somebody want to go to a location where somebody else is there? What would an ideal hashing function do from a probability standpoint? What would an ideal hashing function do or want to do from a probability point of view? Anybody? What would you like your hashing function to do in the best case? Again, perfect hashing not possible. We're going to have collisions. Okay? It's part of the game. We're going to have collisions. So what would you want the ideal hashing function to do? I'll set up the scenario here. We have a hashing table. It has, let's say, 1,000 slots. 1,000, okay? And I'm going to have, let's say, 700 or 800 keys. And I'm going to run each of those keys into the hashing function and store them exactly where the hashing function says. If I have a collision, I will take the record temporarily and set it aside. I'm going to say that was a collision. So what do we want our hashing function to do in the ideal case? What do we want our hashing function